There is a rock in the North Sea called Helgoland. It sits about 40 miles off the German coast, a small slab of red sandstone with cliffs on one side and almost nothing growing on it. No forests and barely a tree anywhere. In early summer, when the mainland is thick with pollen and the fields are heavy with it, Helgoland stays clean, because the wind comes off open water in every direction and carries nothing with it but salt. In the first week of June in 1925, a 23-year-old man got off a boat onto that island with his face so swollen he could barely see out of his own eyes. His name was Werner Heisenberg, and he had hay fever so severe that his landlady in Göttingen had taken one look at him and assumed he had been beaten. He had asked his professor for 2 weeks away. He had chosen Helgoland for one reason, which was that nothing grew there. He walked. He swam in cold water, the swelling went down. And with nobody to talk to and nothing to look at except gray sea and red rock, he went back to the problem that had been quietly ruining his year. The problem was this. For 25 years, physics had been carrying around a small, ugly, unexplained fact, and every attempt to build a proper theory on top of it had failed. People had tried to picture the inside of an atom as a tiny solar system, with electrons going around the nucleus like planets, and it did not work. The pictures kept producing numbers that did not match what laboratories were measuring. Heisenberg, sitting on that empty island, made a decision that sounds almost like a spiritual one. He decided to stop picturing anything at all. If you cannot see an electron, he reasoned, then stop describing where the electron is. Describe only what you can actually measure, the light that comes out, the brightness of it, the colors. Build the mathematics only out of the things a laboratory can put a number on, and let go of the little orbiting ball entirely, because the little orbiting ball was never something anyone had seen. It was a picture people had drawn to feel comfortable. So he built a strange kind of arithmetic out of measurable quantities, and one night, late, alone in a rented room on a rock in the North Sea, he sat down to check whether his scheme conserved energy. If it did not, the whole thing was worthless and he had wasted his holiday. He worked through it. He kept making mistakes because it was 3 a.m. and his hands were unsteady. And the numbers came out right. He wrote later that in that moment he had the feeling of looking through the surface of atomic phenomena to a strangely beautiful interior underneath, and that he felt almost dizzy at the thought that he was now supposed to examine this wealth of mathematical structure that nature had spread out in front of him. He also wrote that he was too excited to sleep, so he left the house, walked to the southern tip of the island, climbed a rock that stuck out over the sea, and waited there for the sun to come up. That last part is probably not true. He wrote it more than 40 years later in a memoir, and historians who have gone through the letters and the dates treat the sunrise as something he added afterwards, the way we all tidy up the best night of our lives when we tell it again. The mathematics is documented. The paper is dated. The rock and the sunrise are the part he gave himself. I like that it is uncertain. It suits the subject, because what that young man found on that island became the theory that tells us, in the most precise language human beings have ever built, that the world underneath is not made of little solid things sitting in definite places, and that certainty of the kind we grew up expecting is simply not on offer, not because our instruments are bad, because the world is not built that way. Tonight we are going to walk through that theory slowly, in the dark, with no hurry at all. This is quantum physics, and it has a reputation for being impossible, and that reputation is half earned and half nonsense. The mathematics is genuinely hard, and I am not going to put any of it in front of you. But the ideas underneath, the actual strange facts about how the world is put together, can be told in plain language, and they are some of the most beautiful things human beings have ever found out. The story runs for about 125 years, and the cast is extraordinary. There is a solemn, conservative German professor who accidentally started a revolution he spent the rest of his life wishing he could take back, and who then lost almost everything a person can lose. There is Einstein, who gave the theory one of its founding ideas, took a Nobel Prize for it, and then spent 30 years trying to prove it was incomplete, arguing with his closest friend about it across a dozen countries and 4 decades. There is a Danish physicist so difficult to understand when he spoke that his own students compared listening to him to trying to hear a man mumbling behind a closed door, and who dissolved 2 Nobel medals in acid to hide them from the Nazis. There is an Austrian who worked out the central equation of the theory during a Christmas holiday in the Alps with a mistress whose name nobody has ever learned. There is an Englishman so silent that his colleagues invented a unit of measurement, 1 word per hour, and named it after him, and who found antimatter by taking his own equation seriously when everybody told him not to. There is an Austrian with a tongue so cruel that the worst insult in physics is still a thing he said. There is a young Indian physicist in Dhaka whose paper was rejected, who mailed it to Einstein with an apologetic letter, and who ended up with a whole class of the universe's particles named after him. There is a quiet man from Belfast who settled the deepest argument in the theory in his spare time. And there is a graduate student who proposed that the universe is constantly splitting into copies, was patted on the head and ignored, left physics forever, drank himself to death at 51, and asked that his ashes be put out with the rubbish. His family did what he asked. Along the way, we are going to understand, properly and without any equations, what the word quantum actually means, and why it turns out that energy comes in grains, like sand, rather than like syrup. We are going to walk through the experiment that Richard Feynman called the only mystery in the whole subject, and see exactly where the strangeness lives. We will find out what the uncertainty principle really says, which is not what you have been told. It is not about clumsy instruments knocking things around. It is stranger and quieter than that. We will find out that Schrodinger's cat was a joke. He invented it to make fun of the theory, and it has been quoted back at him for 90 years as though he meant it seriously, which may be the most complete misreading any scientist has ever suffered. We will look at entanglement, the thing Einstein called spooky action at a distance, and we will be very careful about it, because entanglement is the single most misrepresented idea in modern physics, and I want you to leave tonight knowing exactly what it can and cannot do. And then we will come back down to earth, into your own house and your own body, because the sun outside is shining tonight for a reason that is purely quantum, and the light that fell on you today spent a very long time getting out. Your phone, your laptop, the lead bulb in your lamp, the hospital scanner, the satellites that know where you are. None of them could have been designed without this theory. The chair you sit on holds you up because of a rule discovered in 1925 about how electrons refuse to share. And there is decent evidence that a robin flying south in autumn is navigating using a quantum effect happening in a protein in its eye. You do not need to keep any of this. There is nothing to remember, and nobody is going to ask. If you go under somewhere in the middle of the Alps with Schrodinger, or halfway through the argument between Bohr and Einstein, then this has worked exactly as intended. Let your jaw loosen. Let your shoulders drop away from your ears. Let your breathing go slow and low in your belly, and we will start where it started, which is not on that island, and not with anything anyone was hoping to find. It starts with a light bulb problem. A perfectly practical, boring, industrial light bulb problem, and a 52-year-old professor in Berlin who solved it in a way that horrified him. His name was Max Planck, and he was, by temperament, the least likely revolutionary physics has ever produced. Planck was a formal, courteous, deeply serious man from a long line of pastors and lawyers and professors. He wore the black frock coat. He played the piano beautifully, well enough that he had once seriously considered music as a career. He believed in the permanence of physical law with something close to religious conviction. And he chose physics precisely because it seemed to him the most permanent thing there was, which makes the beginning of his career quite funny. When he was 17, in 1874, Planck went to the University of Munich and asked a physics professor named Philipp von Jolly what he should study. Jolly told him not to bother with physics. He told him the subject was essentially finished. Everything important had been discovered, and all that was left was to fill in a few decimal places here and there. Planck said that was fine. He was not looking to discover new things. He wanted to understand the things that were already known. He went into physics anyway, and 26 years later he broke it open. The problem he was working on had a very unglamorous origin. German industry wanted better standards for electric lighting, and to do that you need to understand exactly how much light a hot object gives off at each color. Heat a poker in a fire and you know roughly what happens. It goes dull red, then orange, then a hot yellow-white. Every hot object does this. The color of the glow depends on the temperature and almost nothing else, which is why blacksmiths and glassblowers have always been able to judge heat by eye, and why we can tell the temperature of a star we will never visit just by looking at its color. So physicists wanted a formula. Give me the temperature, and I will tell you exactly how much light comes out at every wavelength. It sounds like the kind of thing that ought to be tidy. It was not tidy at all. What came out of the mathematics was a disaster. When physicists used the best theory available at the time, which was the beautiful, established, thoroughly tested physics of Newton and Maxwell, the formula they got worked fine for the low frequencies, the reds and the infrared. And then it went insane. As you moved toward the higher frequencies, toward the blue and the ultraviolet, the amount of predicted energy climbed and never stopped climbing. The theory said that any warm object, anything at all, your radiator, a cup of tea, your own body, should be blasting out an infinite amount of ultraviolet energy in every direction, which is not what happens. If it were, opening the oven door would sterilize the room and everyone in it. This was later given a name that sounds like a small apocalypse, the ultraviolet catastrophe, and it deserved the drama, because it was not a small error at the edges. It was the physics of the 19th century, applied carefully and correctly, producing an answer of infinity where the answer is obviously a finite and rather modest number. When a theory gives you infinity, the theory is telling you that one of your assumptions is wrong at the root. Planck spent 6 years on it. He tried everything respectable first, and everything respectable failed. And then, in the autumn of 1900, he did something he described afterwards as an act of desperation. He assumed that the hot object could not give off energy in any amount it liked. Up to that point, everybody had assumed energy was smooth, continuous, like water, which you can pour out in any quantity at all. A liter, a spoonful, a drop, half a drop, whatever you want, with no smallest possible amount. Planck's move was to assume that energy comes out in lumps, fixed, indivisible packets, and the size of the packet depends on the frequency of the light. High-frequency light, the blues and the ultraviolets, comes in expensive packets. Low-frequency light, the reds and the infrared, comes in cheap ones. Think of it as money instead of water. If energy is water, a warm object can trickle out any amount at all, including tiny amounts at very high frequencies, and if you add up all those trickles across all the infinite frequencies available, you get infinity. But if energy is money, and the price of a single blue packet is high, and the object only has so much heat to spend, then it simply cannot afford to emit many blue packets. It has no way to pay, and the ultraviolet ones cost even more, so it emits almost none of those at all. The infinity vanishes, not because you patched the formula, but because the object is now shopping with coins instead of pouring from a jug, and there is no such thing as half a coin. Planck presented the derivation to the German Physical Society in Berlin on the 14th of December, 1900, and that afternoon is usually called the birthday of quantum theory. The size of the coin turned out to be governed by a number that appears in his formula, a fantastically small number, about 6.6 times 10 to the minus 34 in the standard units. It is now called Planck's constant, written as a lowercase h, and it is one of the handful of numbers that seem to be built into the fabric of the universe. It sets the graininess of reality. If it were bigger, the world would be visibly lumpy. If it were zero, everything we are going to talk about tonight would vanish, and the world would be smooth and classical and, as far as anyone can tell, dead now. Here's the part that makes Planck such a strange hero. He did not believe it. He thought it was a trick, a piece of mathematical bookkeeping that happened to produce the right answer, the way you can sometimes get the right total by adding up the wrong things twice. He assumed that someone, probably him, would eventually find a proper explanation underneath it, one that put energy back the way God and Newton had intended it, smooth and continuous. He spent years trying to do exactly that, trying to undiscover his own discovery, and he failed. Because it was true. Helga Krog, one of the historians of the period, called him a reluctant revolutionary, and that is precisely right. Planck did not want a revolution. He walked into one because he was honest enough to publish an answer he hated. Later in life, when he had watched a generation of younger men accept his idea while his own contemporaries went on rejecting it to the grave, Planck wrote a line that has become one of the most quoted observations about how science actually moves. A new scientific truth, he said, does not triumph by convincing its opponents and making them see the light. It triumphs because its opponents eventually die, and a new generation grows up that is familiar with it. People usually shorten that to science advances one funeral at a time, which is funnier and much colder. Planck's own version is sadder and more forgiving, and if you have read anything about his life, you understand why he might have written it that way. Because the 20th century took Planck apart piece by piece. His first wife, Marie, died in 1909. His eldest son, Carl, was killed at Verdun in 1916. His daughter, Grete, died in childbirth in 1917. Her twin sister, Emma, later married Grete's widower, and then died in childbirth herself in 1919. Both granddaughters survived, and each was named after the mother who had died having her. In 1944, his house in Berlin was destroyed in a bombing raid, and his scientific library and his correspondence with it. And then, in that same year, his youngest son Erwin, the one who was left, was arrested for involvement in the July plot to kill Hitler. Planck, by then 86 years old, wrote personally to Hitler asking for clemency for his son. It was refused. Erwin Planck was hanged at Plötzensee prison in Berlin in January of 1945, a few months before the war ended. His death certificate was falsified to say that his parents were unknown. There is a detail from the good years that I keep thinking about. Before all of it, in the 1920s, Planck used to hold musical evenings at his house in Berlin. Planck at the piano, Einstein on the violin, and Erwin, the son, on cello. Planck said afterwards that Erwin's death had taken away his will to live. He died in 1947 at 89 in Göttingen. The unit of the smallest possible action in the universe is named after him. So is Germany's largest research organization. He would probably have preferred the family. Planck had put the grain into physics and then tried to explain it away. It took someone with no reverence at all for the furniture to pick it up and treat it as real. In 1905, a 26-year-old patent clerk in Bern named Albert Einstein published 4 papers in a single year, any one of which would have made a career. One of them was special relativity. One of them proved atoms exist. And one of them, the first one he sent off that year, was about light. Einstein looked at Planck's packets and asked an obvious, dangerous question. What if the packets are not a bookkeeping trick about how hot objects emit? What if light itself is made of packets, all the time, everywhere? What if a beam of light is not a smooth wave at all, but a hail of tiny separate parcels of energy? This was close to heresy. The wave nature of light was not a hunch. It had been demonstrated a century earlier. It explained interference and diffraction and the colors in a soap bubble, and Maxwell's equations, which we met when we talked about electricity, had shown light to be a traveling ripple of electric and magnetic fields. Saying light was made of little lumps sounded like going backwards 200 years, back to Newton's corpuscles. But Einstein had a specific piece of evidence, and it was a small, stubborn laboratory result that nobody could explain. If you shine light on a piece of metal, the light can knock electrons out of the metal. That is the photoelectric effect, and it is the reason automatic doors and old light meters and, in a distant way, solar panels work at all. The puzzle was in the details. Common sense says a brighter light should knock the electrons out harder. More energy going in, more energy coming out. That is how waves work. A bigger ocean wave hits the seawall harder. That is not what happens. What happens is that the color of the light decides whether anything happens at all. Shine a dim blue light on the metal, and electrons come flying off immediately. Shine a blindingly bright red light on the same metal, as bright as you like, for as long as you like, and nothing comes off. Not fewer electrons. None. And if you increase the brightness of the blue light, you get more electrons out, but each one comes out with exactly the same energy as before. Einstein's explanation is so clean it is almost anticlimactic. Light arrives as individual packets, and each electron gets hit by one packet, one at a time. The energy of a packet depends only on the color. A blue packet is a hard shove. A red packet is a gentle nudge. To knock an electron out of the metal, you need a shove above a certain size, and no number of gentle nudges will add up to it, because the electron does not save them. It gets hit once, and either that one hit is enough or it is not. Making the red light brighter means sending more red packets. It does not make any individual packet stronger. It is like trying to knock down a door by throwing more and more ping-pong balls at it. 1,000 ping-pong balls a second is a lot of ping-pong balls, and the door is fine. One brick, and the door is not fine. The color of light sets whether you are throwing ping-pong balls or bricks, and the brightness only sets how many per second. Those packets were later given a name. Photons, and this is the paper that won Einstein the Nobel Prize, awarded in 1921, cited specifically for his discovery of the law of the photoelectric effect, not relativity. Relativity was still considered too controversial by the committee, which leaves us with a beautiful irony sitting right at the front of this story. The man who would spend the last 30 years of his life arguing that quantum theory could not possibly be the final word, who called it incomplete and said its picture of reality was unacceptable, holds a Nobel Prize for one of the founding papers of quantum theory. He did not stumble into it. He saw further into the quantum nature of light in 1905 than anyone else alive. And then he did not like where it went. We will come back to that argument later tonight, because it lasted 30 years and it is the best argument in the history of science. Copenhagen, 1913. A 27-year-old Dane named Niels Bohr had a different problem, and it was worse than Planck's, because it was about whether matter should exist at all. By this point, everyone accepted that an atom had a small, heavy nucleus in the middle with electrons somewhere around it. Ernest Rutherford had shown that a few years earlier by firing particles at gold foil and watching a small number of them bounce straight back, which he said was as astonishing as firing a naval shell at tissue paper and having it come back and hit you. So the picture was a tiny dense center and mostly empty space. The trouble is that if you take that picture seriously and apply the physics of the time, atoms cannot last. An electron going in a circle is an accelerating electric charge, and accelerating charges radiate energy. So the electron should spray out light, lose energy, and spiral into the nucleus. How long would that take? About 100 millionth of a second. Every atom in the universe should have collapsed almost immediately after forming. You would not be here to worry about it. Nothing would. There was a second problem, and it had been sitting around for 50 years, which is that atoms are picky about color. Take a tube of hydrogen gas and run electricity through it, the way a neon sign works, and it glows. Put that glow through a prism, and instead of a smooth rainbow you get a small number of sharp, separate colored lines with darkness in between. Always the same lines in the same places everywhere in the universe. Hydrogen has its set. Sodium has its own, which is why a street lamp with sodium in it glows that particular orange, and why throwing salt in a fire turns the flame yellow. Every element has its own private set of lines. It is a fingerprint, and it is why we can point a telescope at a star trillions of miles away and tell you what it is made of. We have never been there, we never will, and we know its chemistry from its colors. Nobody knew why. It was like discovering that every piano in the world can only play 7 specific notes and refuses to play anything in between, and having no idea why. Bohr put the two problems together and made a move as bold as Planck's and much more visual. He said the electron cannot be anywhere it likes. It can only occupy certain allowed levels around the nucleus, at certain energies, and in those levels. For reasons he could not explain, it simply does not radiate. It sits there, and it is stable. And when an atom emits light, what happens is that the electron drops from a higher allowed level to a lower one, and the difference in energy comes out as a single photon, which means the color of that photon is set exactly by the gap between two levels. The levels are fixed. The gaps are fixed. So the colors are fixed. That is the fingerprint. That is why hydrogen always gives you the same lines. The bottom level is the floor. There is nowhere below it to fall. That is why the atom does not collapse and why you exist. It is worth sitting with how much this explains at once. Why matter is stable, why fire has color, and why different things burn different colors, which is the whole of fireworks. Why the neon sign in a shop window is that particular red and the argon one is that particular blue. Why sodium lamps are orange. Why a laser is one exact color. Why we can read the composition of stars and of the atmospheres of planets around other stars from a smear of light. All of it comes from electrons being allowed only certain rungs on a ladder. Bohr's model was not the final answer, and he knew it. It was a set of rules that worked, bolted onto physics that said they should not. It gets hydrogen beautifully right and then struggles with anything more complicated. The modern picture, which we will get to, replaces the neat orbits with something much fuzzier. But it broke the problem open, and it earned him the 1922 Nobel Prize. More than that, it made Bohr into the center of gravity of the whole subject. He founded an institute in Copenhagen in 1921, and for the next 15 years, if you were a brilliant young physicist anywhere in Europe, you went there. Heisenberg went. Pauli went. Everybody went. Bohr would take them for long walks, and talk, and revise his own sentences endlessly while he talked, and mumble so badly that people leaned in and still could not follow him. He wrote the way he talked, drafting and redrafting single paragraphs for days. There are a lot of Bohr stories. Most of them are true. One of the best comes from the physicist George Gamow, who described visiting Bohr's country cottage and seeing a horseshoe nailed above the door. Gamow asked him whether a scientist of his standing really believed a horseshoe brought good luck. Bohr said no. Of course he did not believe in the superstition. But he had heard, he said, that it works even if you do not believe in it. Another one is true and much darker. When Germany occupied Denmark in April of 1940, there were 2 Nobel medals sitting in Bohr's institute that should not have been there. They belonged to 2 German laureates, Max von Laue and James Franck, who had sent them to Copenhagen for safekeeping, because taking gold out of Nazi Germany was a serious crime, and both medals had the owner's name engraved on them. Somebody described them as 2 death warrants in a drawer. Bohr wanted to bury them in the garden. A Hungarian chemist working at the institute, George de Hevesy, pointed out that the Germans would dig up the garden. So de Hevesy did the only other thing a chemist could do. He dissolved both metals in a mixture of acids called aqua regia, one of the very few things that will dissolve gold, and left the resulting orange liquid in an unlabeled jar on a shelf in the laboratory. German officers searched the institute. They walked past the jar. After the war, de Hevesy precipitated the gold back out of the solution, sent it to Stockholm, and the Nobel Foundation recast the medals and presented them to von Lau and Frank again in 1952. Now, one Bohr story you have almost certainly heard is not true, and I would rather give you the real one. People love to say that the Carlsberg brewery ran a pipe of free beer directly into Bohr's house, so he never ran out. It is a lovely image, and it has been repeated everywhere. The director of the Niels Bohr archive has called it an urban myth, or at best a joke made by his contemporaries that got taken literally. What is true is that Carlsberg owned a grand house next to the brewery, built by the founder, which was given for life to a distinguished Dane, and from 1932 that Dane was Bohr. So he lived next door to a brewery in a mansion the brewery paid for. No pipe. The next step came from an aristocrat in a doctoral thesis, and it was so odd that his examiners had no idea what to do with it. Louis de Broglie was a French duke from one of the old families who had come to physics late and sideways. In 1924, he submitted a thesis at the Sorbonne with a suggestion in it that must have looked, to a committee of respectable physicists, like the work of someone who had lost the thread. Einstein had shown that light, which everyone knew was a wave, also behaves like particles. De Broglie's idea was to run that in reverse. If waves can act like particles, then perhaps particles can act like waves. Perhaps an electron, which everyone was treating as a tiny lump of matter, has a wavelength. Not that it is riding on a wave, that it is one, in some sense that nobody could yet make precise. And he gave a formula for the wavelength, and the formula has Planck's constant sitting in it, which is why nobody had ever noticed this. Planck's constant is minuscule, so the wavelength of anything big enough to see is unimaginably tiny, far smaller than an atom, far too small to have any observable effect. You have a wavelength right now, lying in bed. It is so small that the number is meaningless. But an electron is light enough that its wavelength comes out around the size of an atom, and at that size it matters enormously. The thesis committee, which included Jean Perrin and de Broglie's supervisor, Paul Langevin, could see the elegance and could not tell whether it was physics or poetry. One of them admitted later that he had not believed the waves were real. Langevin, hedging, sent a copy to Einstein and asked what he thought. Einstein wrote back in December of 1924. He said de Broglie had lifted a corner of the great veil. Writing to Lorentz the same day, he called it the first weak ray of light on the worst of all our physics puzzles. De Broglie got his doctorate. 3 years later, in 1927, 2 separate groups confirmed it experimentally. Clinton Davison and Lester Germer in the United States, and George Paget Thomson in Scotland, fired electrons at crystals and got the pattern you get from waves, not the pattern you get from bullets. Electrons diffract. They interfere. They behave, under the right conditions, exactly like ripples. There is a small, delicious footnote there. George Paget Thomson won a share of the Nobel Prize for proving that the electron is a wave. His father, J. Thomson, had won a Nobel Prize 30 years earlier for proving that the electron is a particle. They were both right. Neither of them was wrong. That is the kind of subject this is. De Broglie won the 1929 Nobel Prize for a PhD thesis, which is close to unique. Now everything happens at once. Between the summer of 1925 and the spring of 1926, in the space of about 9 months, the whole theory arrived. 2 completely different versions of it, invented independently by 2 men who could not stand each other's approach, which then turned out to be the same theory wearing different clothes. The first one we have already seen. Heisenberg on Helgoland refusing to picture the electron, building his arithmetic out of measurable quantities only. He brought it back to Göttingen, and his professor Max Born recognized the strange multiplication rules Heisenberg had invented as something mathematicians already knew about, called matrices. Born and a young colleague named Pascual Jordan worked it into a full system with Heisenberg over the following months. It got the name matrix mechanics. It was powerful, it was correct, and almost nobody could use it, because it was abstract to the point of cruelty, and it deliberately refused to give you any picture of what was going on. Physicists hated it, not because it was wrong, because it left them with nothing to see. And then, over Christmas of 1925, a 38-year-old Austrian professor went on holiday to the Alps and came back with a picture. Erwin Schrodinger was, by the standards of the profession, a scandal. He had an open marriage with his wife Annie, which was not the scandal, since plenty of people did. The scandal was how open. He kept a diary of his affairs. He fell in love constantly and enormously. He would go on to live in Dublin during the war in a household with his wife and his mistress and the child he had with the mistress, which the Irish establishment found difficult. At the end of December 1925, he went up to Arosa, a resort in the Swiss Alps, and stayed at a villa there for a couple of weeks with a woman whose identity nobody has ever established. His notebook from that year is lost. One of his biographers compared her to the Dark Lady of Shakespeare's sonnets. She was there, she mattered, and we will never know her name. And in those 2 weeks, Schrodinger wrote down the equation. The prompt had come from de Broglie's thesis, which he had read and been struck by. A colleague, Peter Debye, had made an offhand remark at a seminar that if you are going to talk about matter waves, then you ought to have a wave equation for them, the way we have wave equations for sound and for light. Schrodinger took the remark seriously, went up a mountain with a lover, and produced one. His friend the mathematician Hermann Weyl, who knew all the parties involved rather too well, described the whole business as a late erotic outburst. The Schrodinger equation is the central equation of quantum mechanics, and it is to this subject roughly what Newton's laws are to ordinary mechanics. Give it a situation, an electron near a nucleus, an atom in a magnetic field, whatever you like, and it tells you how the wave associated with that system develops over time. Feed it a hydrogen atom, and Bohr's energy levels fall out of it naturally, not as a rule bolted on from outside, but as a consequence, the way the allowed notes of a guitar string fall out of the fact that both ends are fixed. A string of a given length can only vibrate in certain patterns. An electron bound to a nucleus can only exist in certain patterns. Same reason. That is why the ladder has rungs. Physicists were enormously relieved. Here was something they could draw, something continuous and smooth and familiar, waves in 3 dimensions, mathematics they had been taught. Within months, Schrodinger and others had proved that his wave mechanics and Heisenberg's matrix mechanics, which looked nothing alike, made identical predictions. They were the same theory. 2 people had walked into the same room through different doors, one of them refusing to picture anything, the other picturing everything. Heisenberg was not gracious about it. He wrote to Pauli that the more he thought about the physical part of Schrodinger's theory, the more disgusting he found it. And then came the question that has never been fully answered, and that everything else tonight hangs on. What is the wave a wave of? A sound wave is a wave of air pressure. An ocean wave is a wave of water. Light is a wave of electric and magnetic field. Schrodinger himself hoped, at first, that his wave was the electron smeared out, that the particle was really a little cloud of stuff and the wave described its shape. That did not survive contact with the evidence. When you actually go looking for an electron, you never find a smear. You find a whole electron, in one place, all at once. The answer came from Max Born in 1926, and it is the point where the theory stops being strange in a comfortable way and starts being strange in a way that has kept people awake for a century. Born proposed that the wave is not made of anything physical at all. It is a wave of probability. Where the wave is large, you are likely to find the particle. Where it is small, you are unlikely to. The wave tells you the odds. That sounds harmless. It is not harmless. It means the theory, at its foundation, does not tell you what will happen. It tells you what might happen, and with what likelihood, and that is all it will ever tell you, and as far as anyone has ever been able to demonstrate. The shortfall is not in our knowledge. It is in the world. Bohr got a Nobel Prize for that single insight. He got it in 1954, 28 years late. And it is exactly this, the probability, the dice, that Einstein could not accept, from the moment he read it until the day he died. Before we get to the argument, we should look directly at the strangeness, because so far I have been describing it from the side. There is one experiment that puts it right in front of you, and Richard Feynman, who understood this subject as well as anyone ever has, said it contains the only mystery. He said you cannot explain it away, and that the whole of quantum mechanics is really just this, and that if you understand what is happening here, you understand everything difficult about the theory. It is called the double slit experiment, and the equipment is almost insultingly simple. Take a barrier with two narrow parallel slits cut in it. Put a screen behind the barrier that records whatever hits it. Then fire things at the barrier from the front and see what pattern builds up on the screen. Start with something ordinary. Say you are firing paint pellets. Most of them hit the barrier and stop. Some go through the left slit and some go through the right slit, and on the screen behind you get two stripes of paint, one lined up behind each slit. Roughly, that is what particles do. No surprise anywhere. Now do it with water waves. A wave rolls up to the barrier and passes through both slits at once. And out the back of each slit a new circular ripple spreads. Those two sets of ripples run into each other. In some places, a crest from the left meets a crest from the right, and they add up into a bigger crest. In other places, a crest from the left meets a trough from the right, and they cancel out into flat, calm water. So along the far wall, you get an alternating pattern. Big, nothing, big, nothing, big. That striped pattern is called an interference pattern, and it is the unmistakable signature of a wave. If you see it, waves went through. There is no other way to make it. Now do the experiment with electrons. Fire a stream of electrons at the two slits, and on the screen behind you get the interference pattern. Bands, which is already odd, because electrons are supposed to be particles, but fine. De Broglie told us electrons have a wavelength, so perhaps the stream of electrons is behaving as a wave, and the individual electrons are jostling each other into that pattern somehow. So you turn the source down. Right down. So low that only one electron goes through the whole apparatus at a time, and the next one is not released until the previous one has already hit the screen. There is never more than one electron in the machine. There is nothing for it to jostle against. Each electron arrives at the screen as a single dot. One dot, one place, a particle every time. Nobody ever sees half an electron. But the dots do not pile up into two stripes. Leave it running for an hour, and the dots slowly fill in the interference pattern, band by band, including places where an electron never lands at all. Which means that a single electron, going through the apparatus completely alone, somehow arrives at the screen carrying information about both slits. If you close the right slit, the pattern changes. So the electron that went through, alone, was affected by whether the other slit was open, even though the electron is one thing and it is supposed to go through one hole. At this point, the natural response is the right one. You want to catch it. You want to put a detector at the slits and see which one each electron actually goes through. So you do that. You put a detector at each slit that registers when an electron passes, and it works. The detector tells you every time, cleanly, left, right, right, left. Each electron goes through exactly one slit, like a sensible object. No electron is ever detected going through both. And the interference pattern disappears. The instant you have which-way information, the bands vanish, and you get the two plain stripes you would get from paint pellets. Turn the detector off, and the bands come back. That is the mystery. The result depends on what you know. not on what you do to the electron in any crude sense of hitting it or heating it or pushing it, but on whether the information about which path it took exists anywhere in the world. When the path is not determined, you get the wave behavior. When it is determined, you get the particle behavior. The electron behaves as though it went both ways when nothing distinguished the two ways, and as though it went one way when something did. This has been done with photons, with electrons, with neutrons, with whole atoms, and with large molecules containing hundreds and even thousands of atoms. The bigger the object, the harder it is to protect it from being disturbed by its surroundings, which is why you have never seen yourself interfere while walking through a doorway. But the effect has never broken. Every time somebody builds a bigger version, it works. Now, a warning, because this is where a great deal of nonsense gets attached to physics. There are more elaborate versions of the experiment with names like delayed choice and quantum eraser, in which the decision to record the which way information is made after the particle has already gone through the slits, or in which the information is recorded and then scrambled beyond recovery. The results are consistent and beautiful and, correctly understood, they say the same thing the plain version says. The pattern depends on whether the path information is available in the final analysis. They do not show that the future changes the past. They do not show that human consciousness reaches back in time and alters what already happened. Whenever you see the quantum eraser being used to sell you a book about the power of your mind to shape reality, the argument has gone wrong somewhere between the laboratory and the paperback. The full accounting always works out, and no signal ever travels backwards, and no experiment has ever needed a mind to be present. What the double slit shows is smaller and much stranger than the mystical reading. It shows that between being emitted and being detected, an electron does not have a definite path, and that the question where was it in between does not have an answer. Not a hidden answer we cannot reach. Feynman's point, which is the honest one, is that there is no mechanism underneath that makes this comfortable. He said nobody understands quantum mechanics, and he meant it as a statement about the current state of human knowledge, not as an invitation to make things up. 2 years after Helgoland, in 1927, Heisenberg found the rule underneath. It is called the uncertainty principle, and it is the most famous idea in the subject and the most consistently mangled. So let me build it up carefully, because the correct version is genuinely beautiful, and the popular version is just an insult to instrument makers. The principle says that certain pairs of properties of an object cannot both have precise values at the same time. The famous pair is position and momentum, where momentum is essentially how fast something is going and in what direction. The more precisely a particle's position is defined, the less precisely its momentum is defined, and the other way round, and there is a hard floor on how well you can do on both at once. That floor is set by Planck's constant, which is why nobody noticed for 300 years. Now, the version you have heard is that this is about measurement being clumsy. To see something you have to bounce light off it, and bouncing light off an electron knocks it around. So the act of looking disturbs what you are looking at, and that is why you cannot know both. That explanation was Heisenberg's own. He introduced it that way in 1927, with a thought experiment about trying to look at an electron through an imaginary microscope using very short wavelength light. And Bohr, who was his mentor, told him he had explained it badly, and they argued about it, and Bohr was right. The disturbance picture is misleading because it makes it sound as though the electron really does have a precise position and a precise momentum, and our clumsy instruments simply cannot get at both. That is not what the theory says. The theory says the electron does not possess a sharp position and a sharp momentum at the same time. There is nothing there to measure. It is not hidden. It is not there. And here is the way to feel it in your body, which requires no physics at all, only music. Think about a note. A pure, sustained note, a violin holding a long A. That note has a very well-defined pitch. You could tune to it, but ask when it happened, and you cannot really answer. because it took time to exist as a note. Pitch is a property of something repeating, and you need many repetitions before the pitch is definite. Shorten the note and the pitch gets fuzzier, and if you shorten it far enough, right down to a single click, it has no pitch at all. A click is very precisely located in time and completely undefined in pitch. A long tone is very precisely defined in pitch and smeared out in time. That trade-off is not a limitation of your ears or of the microphone. It is a mathematical property of waves. Anything wave-like has it. Sound has it. Radio engineers work with it every day, and it is why a radio station needs a band of frequencies rather than a single one to carry a signal that changes. Quantum mechanics says matter is wave-like, so matter inherits the trade-off. Position is where the wave is. Momentum is related to the wavelength, to how tightly the ripples are spaced. And you cannot have a wave that is squeezed into a single point and also has a perfectly definite wavelength, for exactly the same reason that you cannot have a click with a pitch. The uncertainty principle is not a statement about our fumbling. It is a statement about what kind of thing a particle is. There is one more consequence worth having, because it is where this stops being abstract. Because you cannot pin down position and momentum together, you can never have a particle sitting perfectly still in a perfectly definite spot. Perfect stillness is a precise momentum of zero and a precise position at the same time. And the world will not allow it. So everything jitters, always, even at absolute zero, even in principle. That residual motion has a name, zero-point energy, and it is why liquid helium refuses to freeze solid under its own vapor pressure no matter how cold you make it. The atoms will not sit still, because sitting still is forbidden. There is a kind of restlessness built into matter at the bottom. Everything you can see, including the pillow under your head, is quietly humming and cannot stop. Which brings us to a cat that was never in a box, and never in any danger, and was never meant to be taken seriously. By the middle of the 1930s, a standard way of talking about all this had settled in, mostly built by Bohr and Heisenberg and the people around them in Copenhagen, and it became known as the Copenhagen interpretation. It goes roughly like this. Before a measurement, a system is described by the wave, and the wave can contain several possibilities at once, in what is called a superposition. The electron is not secretly in one place. The description that gets the right answers has it in a combination of places. Then you measure, and you get one definite result, and the wave collapses to match it. Now, superposition is not the same as ignorance, and this is the part worth getting right. If I flip a coin and slap it on the back of my hand without looking, the coin is heads or tails, and I do not know which. That is ignorance, and there is nothing spooky about it. A superposition is not that. We know it is not that because of the double slit. If the electron were secretly going through one slit, and we merely did not know which, then the pattern on the screen would be the sum of the two single slit patterns, and it is not. It has bands, including dark bands where electrons land when only one slit is open and stop landing when both are. Opening a second route makes some destinations less likely. Ignorance cannot do that. Only genuine combination can. Erwin Schrodinger found the whole business unacceptable, and in 1935 he wrote a long paper in which he tried to show, by ridicule, how bad it gets when you scale it up. He asked you to imagine a cat sealed in a steel chamber with a small amount of radioactive material, a Geiger counter, a hammer, and a flask of acid. Over the course of an hour, there is a 50-50 chance that a single atom decays. If it decays, the counter trips, the hammer falls, the flask breaks, and the cat dies. If it does not, the cat is fine. The decay of a single atom is a genuinely quantum event, so before you look, the atom is in a superposition of decayed and not decayed. And Schrödinger's point was that the chain of dominoes drags the cat into it. So the honest application of the theory leaves you saying that the cat, a whole living animal, is in a superposition of alive and dead until somebody opens the box. He called this case burlesque. That was his word. He was not proposing it as a wonder of nature. He was proposing it as an absurdity, a way of saying to Bohr, look what your interpretation commits you to. This is obviously ridiculous. Your theory must be missing something. And for 90 years the cat has been quoted back at him as the classic illustration of how weird quantum mechanics is, which is precisely the opposite of the argument he was making. It is as if you told a joke to point out that someone's idea was silly, and history remembered the joke as the idea. The problem he was pointing at, though, is completely real, and it does not have an agreed solution to this day. It is called the measurement problem, and here it is in plain terms. The Schrodinger equation is smooth, deterministic, and it never collapses anything. Left alone, it takes a superposition and evolves it into more superposition forever. But when we measure, we always see exactly one outcome. So somewhere between the equation and the laboratory notebook, something happens that the equation does not describe. What is it? What counts as a measurement? How big does a thing have to be before it stops being in two states at once? Where is the line? There is a large piece of the answer, and it was worked out properly from the 1970s onwards, and it is called decoherence. Nothing in the real world is ever isolated. An object is constantly being touched by its surroundings. Air molecules bump into it. Photons bounce off it. Heat radiates from it. Every one of those interactions carries away a little information about where the object is and what it is doing, and once that information has leaked into the environment, the delicate relationship between the different parts of the superposition is destroyed, and the interference vanishes. Decoherence explains why you never see a cat in superposition, and the numbers are extraordinary. For something the size of a dust grain sitting in ordinary air at room temperature, the interference is destroyed in something like a billionth of a billionth of a billionth of a second. A cat is astronomically worse. The superposition does not need to be broken by an observer, because the air in the box has already broken it, roughly instantly, before anyone gets anywhere near the lid. This is also why quantum computers have to be shielded and refrigerated to within a fraction of a degree of absolute zero. Keeping something in superposition is not easy. It is the hardest engineering problem in the field, and the universe is constantly trying to spoil it. But be careful, because decoherence is often oversold. It explains why we do not see superpositions of big things. It explains why the world looks classical. What it does not do is explain why you get this outcome rather than that one. It turns a superposition into something that behaves like ordinary ignorance, a list of possibilities with probabilities attached, and that is a great deal of progress. It does not tell you why the coin came up heads. The measurement problem is narrowed, not closed, which leaves the door open, and a great many people have walked through it, and we will come back to what they found in a while. First, though, there is a myth to kill, because it has done more damage than all the others put together. You will hear, constantly, that quantum mechanics proves that consciousness creates reality, that the universe does not exist until a mind observes it, that the double slit shows the electron knows when it is being watched. There are films and books and entire wellness industries built on this, and it is worth being precise about why it is wrong. The word observation in a physics paper means an interaction that produces a record. It means the particle got entangled with something bigger, something with many degrees of freedom, in a way that carries off information about what it did. A photographic plate observes. A Geiger counter observes. A stray air molecule observes. A rock observes. None of these things is conscious, and the experiments work perfectly well when nobody is in the room and the data is read off a hard drive next Tuesday. There was a period, early on, when a few serious physicists did wonder whether consciousness had to enter somewhere, because the collapse had to happen somewhere and the chain of instruments seemed to go on forever. Eugene Wigner took it seriously for a while and then abandoned it. Decoherence took most of the air out of the idea. because it showed the environment does the work long before a human being turns up. It is not a mainstream position today, so when someone tells you that quantum physics means your thoughts shape the universe, or that you can heal yourself by aligning your quantum field, they are not describing anything in the theory. The theory is a set of rules for calculating probabilities, and it works whether or not anyone is thinking about it, and it worked for 13 billion years before there was anyone to think. The real strangeness does not need any help. It is quite sufficient on its own. Brussels, October 1927. 29 physicists sat for a photograph on the steps of a building at the Solvay conference, and it is probably the most concentrated gathering of scientific talent ever assembled in one room. 17 of the people in that photograph either had a Nobel Prize or would get one. Marie Curie is in it, and she had 2. They were there to argue about exactly what we have just been through. On one side, Bohr and Heisenberg, and Born and Pauli, arguing that the theory was finished. Probability all the way down. There is no deeper level. Stop asking. On the other side, Einstein and Schrodinger and de Broglie and a handful of others saying that a theory which only gives you odds cannot be the last word about a world that, when you look at it, always does one specific thing. Einstein's objection is often described as stubbornness, or as an old man failing to keep up, and neither is fair. He was 48 in 1927 and at the height of his powers, and his objection was philosophical in the best sense. He believed there was a real world out there with definite properties, whether or not anyone was looking at it, and that the job of physics was to describe that world. Quantum mechanics, as Bohr presented it, seemed to say that properties do not exist until they are measured, and that the fundamental description of nature is a betting slip. The line everyone knows comes from a letter he wrote to Max Born in December of 1926. People usually quote it as, "God does not play dice," which is close enough but flattens it. What he actually wrote was that quantum mechanics is certainly imposing, but that an inner voice told him it was not yet the real thing. "The theory says a lot," he wrote, "but it does not really bring us any closer to the secret of the old one." And then, I at any rate am convinced that he does not throw dice. He was not appealing to religion. Einstein's God was Spinoza's, a name for the order of nature, and what he was really saying is that he could not believe the deepest layer of the world was random. So at Solvay, and again 3 years later, he came at Bohr with thought experiments. Little machines, imagined in detail, each one designed to beat the uncertainty principle by measuring 2 forbidden things at once. And the pattern of those conferences became legendary. Einstein would produce a new puzzle at breakfast. Bohr would spend the day walking around looking stricken, muttering, and by dinner or by breakfast the next morning, Bohr would have found the flaw. The most famous one came at the 6th Solvay conference in 1930, and it is worth telling properly because of how it ends. Einstein imagined a box with a hole in the side and a shutter over the hole, and the box full of light, and a clock inside connected to the shutter. The clock opens the shutter for a precisely known instant. 1 photon escapes, and the shutter closes. So you know exactly when the photon left. Now weigh the box before and afterwards. Since energy and mass are equivalent, and Einstein of all people knew the exchange rate, weighing the box tells you exactly how much energy the photon carried away. So you have the energy exactly and the time exactly. And there is a version of the uncertainty principle that says you cannot have both. Bohr, by every account of that evening, was badly shaken. Leon Rosenfeld described him going from person to person that night, unable to find an answer, saying that if Einstein was right, it was the end of physics. He did not sleep. In the morning he had it, and the way he had it has been enjoyed by physicists ever since. To weigh the box, you have to let it hang on a spring, and read a pointer against a scale, and that means the box moves up and down a little in the Earth's gravitational field. But general relativity, which Einstein himself had built 15 years earlier, says that a clock runs at a different rate depending on where it sits in a gravitational field. So the moment you weigh the box precisely, the clock inside it has moved, and its rate has changed by an amount you cannot fully know, and the timing of the shutter becomes uncertain by exactly the amount required. Bohr defeated Einstein's attack on quantum mechanics using Einstein's own theory of gravity. Einstein conceded the point. Now, honesty, because this story is told triumphantly and modern historians are less tidy about it. There is good evidence, including a letter from Paul Ehrenfest to Bohr in 1931, that Einstein's real target was never the uncertainty relation at all, and that Bohr won an argument Einstein was not quite having. The deeper worry Einstein was circling around was not about clocks. It was about what happens when two objects have been in contact and then separated, and that worry was about to become the most important idea in the subject. Because 5 years later, Einstein stopped attacking and published. In May of 1935, Einstein, together with two younger colleagues at Princeton, Boris Podolsky and Nathan Rosen, published a short paper with a question for a title. Can quantum mechanical description of physical reality be considered complete? It is universally known by the three initials, EPR. The argument runs like this. Quantum mechanics allows two particles to be created together in such a way that their properties are linked, not merely correlated in the ordinary sense, but described by a single shared wave, so that neither one has its own separate description at all. Schrodinger, reading the paper, coined a word for this in English, and the word was entanglement. He said it was not one, but the characteristic trait of quantum mechanics, the thing that forces its entire departure from classical lines of thought. Take two entangled particles and let them fly apart. One goes to a laboratory in Madrid and the other to a laboratory in Tokyo. Now measure a property of the Madrid particle. Because the two are entangled, the moment you get your result in Madrid, you know with certainty what the corresponding measurement in Tokyo will give, instantly, however far apart they are. And Einstein said, in effect, there are only two ways this can be. Either the Tokyo particle had that property all along, in which case quantum mechanics is incomplete, because quantum mechanics denies the particle had a definite property before measurement, and clearly it did. Or the measurement in Madrid somehow reached across the world and set the property in Tokyo at the moment of measuring, which would require an influence traveling faster than light, and relativity forbids that. To Einstein, the choice was obvious. The first option is boring and sensible. The particles have real properties from the start. Quantum mechanics simply does not track them, and one day a better theory will. He compared it to a pair of gloves. If I put a left glove in one box and a right glove in another, and post one box to Tokyo, then when I open my box in Madrid and see a left glove, I instantly know the Tokyo box has a right one. Nothing traveled. The gloves were always what they were. I just learned something. He wrote to Bohr about the alternative and called it spookhafte Fernwirkung, which everyone translates as spooky action at a distance, and he meant it dismissively. Bohr's response was quick and, by common agreement, extremely hard to follow. Einstein went on thinking he had made an unanswerable point, and most working physicists concluded that the whole thing was philosophy, and got on with calculating. Because the theory kept giving right answers and there was a great deal of chemistry and nuclear physics to be getting on with, and there the question sat for 29 years. Not because it was settled, because nobody could see how you would ever test a question like that. Then a man from Belfast solved it in his spare time. John Stuart Bell was born in 1928 into a working-class family in Belfast, and he left school at 16 because there was no money to keep him there. He got a job as a technician in the physics department at Queen's University, and the staff there liked him enough to lend him books and let him sit in on lectures, and eventually he got in as a student properly. He spent most of his career at CERN in Geneva working on accelerator design and particle theory. That was the day job. The other thing, the thing that made him immortal, he called his hobby. He was careful about it. Foundations of quantum mechanics was not a respectable field in the 1960s. It was where careers went quietly to end. So Bell worked on it on sabbatical, away from the office, in 1963 and 64. What set him off was David Bohm, whose own story is waiting for us later, and who in 1952 had done something everyone said was impossible, namely construct a version of quantum mechanics with real particles following real paths which reproduced all the predictions. Bell said afterwards that in 1952 he saw the impossible done, and what struck him about Bohm's theory was that it had to be explicitly, unashamedly non-local. In Bohm's picture, what happens here really does depend instantly on what is going on over there. So Bell asked the question that nobody had asked: is that non-locality a peculiarity of Bohm's particular theory? Or is any theory that reproduces quantum mechanics forced into it? And in 1964 he proved a theorem and published it in a short-lived journal that almost nobody read, and it is the most profound result in the foundations of physics. Here is what Bell proved in words. Suppose you take Einstein's view. The particles carry their properties with them from the start, like the gloves. Nothing travels faster than light. Call that a local hidden variable theory. Local, because nothing jumps across space instantly. Hidden variables, because the properties are real, but the theory does not currently list them. Bell showed that any theory of that kind, absolutely any theory, no matter how clever, no matter how complicated, has to obey a certain limit. If you measure the two particles along various different angles, and you look at how often the results agree, then a local hidden variable world has a ceiling on how strongly the results can correlate. That ceiling is now called a Bell inequality, and quantum mechanics predicts that in certain arrangements, the correlations go straight past the ceiling. That is the whole thing. It converted a philosophical dispute into an experiment. It meant you could go into a laboratory, make some entangled particles, measure them at various angles, count up the agreements, and find out whether the world is the way Einstein thought it was. There is a number. You measure the number. The number decides. The gloves analogy, incidentally, is where you can feel exactly what Bell did. The gloves explanation is fine for the simple case, and this is why the analogy is so seductive. If you only ever measure the one obvious property, the gloves account works perfectly, and there is no mystery. Bell's genius was to notice that you can measure other things too, at other angles, and to work out that the pattern of agreements across all those angles is where the two pictures split. Gloves can only agree so often. Entangled particles agree more, and no arrangement of gloves, no matter how elaborately you pre-package them, can be made to agree that often. The experiments took time, because they are difficult. The first serious one was done in 1972 by John Clauser and Stuart Friedman at Berkeley, on equipment largely built out of scrounged parts. Clauser had trouble getting anyone to support the work. He said later that he hoped to prove Einstein right, and he was disappointed. The correlations went past the limit. Quantum mechanics won. But there was a loophole, and it was a serious one. In those early setups, the two detectors were set to their measurement angles in advance and stayed that way. So in principle, some slow influence could have traveled from one side of the apparatus to the other at ordinary speeds and coordinated things. Unlikely, but you cannot build a foundation on unlikely. Alain Aspect closed it in 1982 at Orsay, near Paris, with an apparatus that changed the angle of each detector while the photons were already in flight, so fast that no signal traveling at the speed of light could have carried the news from one detector to the other in time. The correlations still exceeded the limit. Then Anton Seilinger's group in Vienna and others spent the following decades closing every remaining loophole, including one that took until 2015 involving whether the detectors were sampling fairly, and one that involved where the random choices of angle came from, which was eventually run using light from distant stars so that the choices had been fixed centuries before the experiment. The result has never wavered. In 2022, the Nobel Prize in Physics went to Alan Aspect, John Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. So Einstein was wrong. Not wrong in the sense of foolish, and not wrong about everything, because he was the one who spotted entanglement in the first place and gave it its shape. He was wrong about which of his two options the universe had chosen. The particles do not carry their answers with them, quietly, the way gloves do. The world is not locally real in the sense he wanted it to be. Somewhere in that sentence something has to give, and physicists still argue about exactly which word. And now the part I promise to be careful about, because it matters. Entanglement cannot be used to send a message. Not slowly. Not at all. This is the single most common misunderstanding in modern physics, and you will see it in films, in novels, in newspaper articles about quantum internet, and it is flatly wrong, and there is a theorem about it called the no communication theorem. Here is why. When you measure your half of an entangled pair in Madrid, what do you get? A random result. That is all. If it is a photon's polarization, you get one of two answers, at random 50-50. Your friend in Tokyo measures her half and gets a random result too. Neither of you can control what you get. Neither of you can look at your own results and tell whether the other person has measured yet, or what they chose to measure, or anything else. Each of you has a list of coin flips. The strangeness only appears when the two of you get together afterwards, over a normal telephone or a normal email, traveling at ordinary speeds, and lay your two lists side by side. Then you see the correlations, and the correlations are stronger than any classical arrangement could produce, and that is the astonishing fact. But you had to send the lists to each other by ordinary means to see it. The mystery lives in the comparison, and the comparison never travels faster than light. So entanglement is not a telephone. It is more like this. Two people are each handed a sealed deck of cards, and no matter how far apart they go, when they turn over the top card at the same moment, their cards match in a way that no prearranged shuffle could achieve. Neither of them can choose what card comes up. Neither can use it to say anything. But the matching itself is real, and it should not be possible, and it is. Which is why quantum teleportation, when you read about it, always includes a boring detail that never makes the headline. To teleport a quantum state from one place to another, you need the entangled pair, and you also need to send two ordinary bits of classical information down a normal channel. Without that phone call, the receiver has garbage. The state does not arrive until the phone call does. Nothing has ever moved faster than light, and nothing in this theory ever will. The honest version is stranger than the science fiction version, and it does not break anything. Let us leave the argument for a while and go and meet two men who found things nobody was looking for. They were both difficult in completely different directions, and between them they explained why matter has structure and why there is a mirror version of everything. The first is Paul Dirac, and he may be the strangest person in this entire story. Dirac was born in Bristol in 1902. His father was Swiss, a French teacher, and by all accounts a domestic tyrant of a very specific kind. He insisted that Paul speak to him only in French at the dinner table, and corrected and punished him for every mistake. Paul found it easier to say nothing. He said much later that this was where his silence came from. He simply stopped talking, and he never really started again. The silence became legendary at Cambridge. His colleagues, who were fond of him in a bewildered way, joked about defining a unit of conversational speed called the Dirac, equal to 1 word per hour. The stories about him are all about literal-mindedness, and they are wonderful. During a lecture, someone in the audience said he did not understand an equation on the board. Dirac said nothing. After a silence, the chairman asked whether he would answer the question, and Dirac said that it had not been a question. It had been a statement. Crossing the Atlantic with Heisenberg in 1929, Dirac watched Heisenberg dancing with young women every evening, and eventually asked him why he danced. Heisenberg said, because nice girls are there. Dirac considered this and then asked how he knew beforehand that the girls were nice. Somebody once told him a story about a novel in which the sun rose twice in one day. And Dirac took the point of the story to be the error and said the book was no good. And with that mind, in 1928, at 25, he did something that Einstein and Bohr and everybody else had failed to do. He wrote down an equation for the electron that worked properly with special relativity. Schrodinger's equation is not relativistic. It works beautifully for electrons moving slowly, which covers a great deal of chemistry, but it does not respect the rules of high-speed motion, and everyone knew a proper version was needed. Dirac found it by insisting on a kind of mathematical beauty and simplicity, and following where it led. The equation immediately did two things nobody expected. It produced the spin of the electron automatically, as a consequence rather than an add-on. Spin had been discovered experimentally a few years earlier and stuck on by hand, and Dirac's equation just handed it over as though it had been obvious all along. And it had extra solutions. Solutions describing a particle with the same mass as the electron and the opposite electric charge. Everyone told him to ignore them. Extra solutions are common in mathematics and usually mean nothing physical. Dirac, after some false starts, decided that his equation was telling him the truth and that there was a particle out there that nobody had ever seen. A positive electron. He said later, one of my favorite lines from any scientist. He said that his equation was smarter than he was. In 1932, Carl Anderson at Caltech was photographing cosmic rays passing through a cloud chamber in a magnetic field, and he found tracks that curved the wrong way. Same mass as an electron. Opposite charge. Exactly what Dirac had predicted from pure mathematics. It was named the positron, and Dirac shared the Nobel Prize the following year. At 31. Antimatter is real, and it turned out not to be an exotic curiosity. Every kind of particle has an antiparticle. When a particle meets its antiparticle, they annihilate, and the whole of their mass turns into energy, which is the most efficient conversion in the universe. And here is the domestic ending to it. If someone you love has ever had a PET scan, a positron emission tomography scan, in a hospital, they were injected with a substance that emits positrons. Dirac's impossible particle, predicted by a silent man following the beauty of an equation in 1928, wanders a few millimeters through human tissue, meets an ordinary electron, annihilates, and produces two photons flying in opposite directions. The scanner catches both and works backwards to the point where they were born. That is how the picture is made. Antimatter is a medical tool now, used thousands of times a day. Dirac nearly turned down his Nobel Prize because he hated publicity so much. Rutherford talked him out of it by pointing out that refusing would generate far more press than accepting. He is commemorated with a stone in Westminster Abbey, near Newton, with his equation carved into it. The second man is Wolfgang Pauli, and if Dirac was silent, Pauli was the opposite, and much more dangerous. Pauli was Austrian, a prodigy who published a definitive review of relativity at 21 that Einstein praised, and he had the most feared critical faculty in physics. He was not simply harsh, he was accurate, which is worse. Physicists called him the conscience of physics, and they sent him their work before publishing precisely because they wanted the worst possible reading, and they knew he would supply it. His most famous line came from reading a paper so bad it did not even manage to be incorrect. Rudolf Peierls recorded him saying that it was not only not right, it was not even wrong. Physicists still use the phrase, "There is no colder thing you can say about an idea." There was also the Pauli effect, which was a running joke that everyone in the field enjoyed keeping alive. Equipment broke when Pauli was near it. Instruments failed, apparatus fell over, glassware shattered, and always in his presence, never in his hands, because he was a theorist and famously incompetent in a laboratory. Pauli himself came to half believe in it and rather enjoyed it. Gamow described it as a kind of second exclusion principle, The rule being that Pauli and a working piece of apparatus cannot occupy the same room, which brings us to the first exclusion principle, and it is the reason you are not currently falling through your bed. In 1925, Pauli was trying to understand why the electrons in an atom arrange themselves the way they do. Bohr had given us a ladder of allowed energy levels, and that explains colors. But it raises a question: why do the electrons not all just drop to the lowest rung and stay there? Everything in nature falls to the lowest available energy. Water runs downhill. Why does a uranium atom with 92 electrons not have all 92 of them piled up in the bottom level? Pauli's answer was a rule with no explanation underneath it at the time. No two electrons in an atom can be in exactly the same quantum state. Once a state is occupied, it is occupied. The next electron has to go somewhere else. So electrons stack. The lowest level fills up, and then the next one has to sit in the level above, and that fills, and so on outwards, and the atoms of heavier elements end up with electrons in progressively larger, higher shells. And that is the periodic table. That is all of chemistry. The chemical behavior of an element is essentially decided by how many electrons are loose in its outermost occupied shell. Elements with a full outer shell are the noble gases, helium and neon and argon, and they are famously unreactive, because they have nothing to offer and no room to take. Elements with one lonely electron in a new shell are the alkali metals, sodium and potassium, and they are violently reactive because that one electron is desperate to leave. The whole shape of the periodic table, the reason it has rows of the length it has, is the stacking pattern that Pauli's rule forces. Every reaction in your body, every bond and every molecule you are made of, the water in your cells, the oxygen in your blood, the shape of your DNA, all of it is downstream of the fact that electrons will not share a state. And it goes further than chemistry, into something you can feel with your hands right now. Why is a table solid? The standard answer people are given is that atoms are made mostly of empty space, with a tiny nucleus and electrons somewhere out there. And that when you push your hand against a table, the electrons in your hand repel the electrons in the table electrically. That is partly true, and it is not the main effect. The main effect is Pauli. When you press two objects together, you are trying to force the electrons of one into the same region and the same states as the electrons of the other, and they will not go. Not because of the electrical repulsion, but because of the exclusion rule itself. To squeeze them together, you would have to promote electrons into higher energy states, and that costs energy, and the cost rises very steeply. That resistance is called degeneracy pressure, and it is what stops your hand passing through the wood. Solidity is a quantum phenomenon. The firmness of the mattress underneath you tonight is a consequence of a rule discovered in 1925 about how electrons refuse to be identical, and on a larger scale, this same stubbornness holds up dead stars. When a star like our sun runs out of fuel, gravity starts crushing it, and there is nothing burning inside to push back. It collapses down to about the size of the Earth, with the mass of the sun, and then it stops. It stops because the electrons inside it have run out of available states and refuse to be squeezed closer. A white dwarf is a star held up against its own gravity by Pauli's exclusion principle. Nothing is burning. Nothing is pushing. The electrons simply will not go, and that is enough to hold up a star. Push harder with a heavier star, and the electrons finally lose and combine with protons, and you get a neutron star, which is held up by the same refusal among neutrons instead. A neutron star is the mass of a sun packed into a sphere the width of a city, and a teaspoon of it would weigh about as much as a mountain. And it is held up by a quantum rule. Push harder still, and even that fails, and you get a black hole. So the same principle that gives you the periodic table and the chemistry of your own body and the solidity of the floor also decides the fate of stars. Very little else in physics ties that much together, and it comes from a man whose colleagues were mostly afraid of him. Pauli has one more story, and it is my favorite in the whole subject, because it is a piece of pure faith. In the 1920s, there was a crisis in the study of radioactive decay. In a process called beta decay, a nucleus emits an electron, and when physicists measured the energies of everything before and after, the numbers did not add up. Energy was missing. Not the same amount every time, which would have been a systematic error. A different amount every time, spread across a range. This was serious enough that Bohr, of all people, was prepared to consider abandoning the conservation of energy at the subatomic scale. That is how bad it was. Bohr was ready to give up one of the most basic accounting rules in all of physics. Pauli would not have it. On the 4th of December, 1930, he wrote an open letter to a meeting of physicists at Tübingen, which he was not attending because he had been invited to a ball in Zurich that night and preferred to go dancing. The letter is addressed, in the original, to dear radioactive ladies and gentlemen. He wrote that he had hit upon a desperate remedy to save the conservation of energy. He proposed that there was a particle nobody had detected, coming out of the nucleus alongside the electron and carrying off the missing energy. It would have to have no electric charge and almost no mass, and it would have to interact with matter so weakly that it could pass through the entire Earth without noticing. He admitted that he did not feel secure enough to publish anything about the idea, and that he could not see how to detect it. And he ended with the line that ought to be on a wall somewhere, that only those who wager can win. He had, he said afterwards, done a terrible thing. He had postulated a particle that could not be detected. He was writing that letter in the middle of the worst year of his life. His mother had killed herself. His marriage had collapsed after a matter of months, his wife having left him for a chemist, about which Pauli said bitterly that if it had been a bullfighter he might have understood it. He was drinking heavily. And around this time he began analysis with Carl Jung in Zurich, which turned into a correspondence lasting more than 20 years about physics and dreams and the mind. Pauli was a serious enough dreamer that hundreds of his dreams became case material in Jung's published work anonymously. The particle he proposed was named the neutrino. It was detected in 1956, 26 years after the letter, by Clyde Cowan and Frederick Raines. Using a nuclear reactor as a source and a tank of liquid as a detector, they sent Pauli a telegram. He is said to have replied, "Everything comes to him who knows how to wait." They are extraordinarily hard to catch because Pauli was right about how weakly they interact. About 60 billion neutrinos from the sun pass through every square centimeter of your body every second, day and night. And at night they arrive by coming up through the entire planet first, because the Earth is essentially transparent to them. In your whole life, a small handful will interact with an atom in your body. The rest go straight through and out the other side and on into space. Pauli died of pancreatic cancer in 1958. He was in room 137 at the hospital in Zurich when he learned the number, and it upset him because the fine structure constant, a mysterious number in physics whose value nobody can explain, is very close to 1 over 137. He had spent years obsessing about it. He is supposed to have said that he would never get out of that room. He did not. There is one more character to meet before we come home to your own house, and his story starts with a letter written by a man who had been turned down. In 1924, a 30-year-old physicist named Satyendra Nath Bose was teaching at the University of Dhaka in what was then British India and is now Bangladesh. He was a long way from the center of things. He had no laboratory and very little contact with the people in Copenhagen and Göttingen and Berlin who were arguing about all this. Bose had found a new way to derive Planck's radiation law, the one we began the night with. His method was strange, and it rested on a single move that turns out to be enormous. He treated the photons as genuinely indistinguishable from one another. That sounds like a small thing. It is not. In ordinary counting, if you have 2 coins and 2 boxes, you count 4 arrangements, because coin A in box 1 with coin B in box 2 is a different arrangement from the reverse. Both counted them as the same arrangement because photons have no identity. There is no photon A and photon B. There is only two photons, and asking which is not a question with an answer. Change the counting and you change the statistics, and out falls Planck's law cleanly, without any of the classical scaffolding that Planck had to work around. Bohr sent the paper to a journal in Britain, and by the account usually given, it was rejected. So he did something that must have taken some nerve. He posted it directly to Albert Einstein in Berlin, with a covering letter dated the 4th of June, 1924, written in English, asking respectfully whether Einstein would read it and give an opinion. He wrote that although he was a complete stranger, he felt no hesitation in making the request. Because we are all your pupils. Einstein read it, understood at once what Bohr had done, translated the paper into German himself, and arranged for it to be published in one of the leading physics journals with a note from him saying that it was an important advance. Then he took the idea further. If photons behave like this, Einstein reasoned, why not atoms of the right kind? And he worked out that if you took a gas of such atoms and cooled it down far enough, something remarkable would happen. Below a certain temperature, the atoms would stop behaving as individuals. They would all fall into the same lowest quantum state at once, and become, in a real sense, a single quantum object, not a crowd of atoms doing the same thing. One thing, spread out, with one shared wave. This was in 1924 and 1925, and it was a prediction with no hope of being tested, because the temperatures required were far below anything anybody could reach. It took 70 years. On the 5th of June, 1995, at a laboratory in Boulder, Colorado, Eric Cornell and Carl Wieman cooled about 2,000 atoms of rubidium down to around 170 billionths of a degree above absolute zero, which is colder than anywhere in deep space, and watched them collapse into a single shared state. The Bose-Einstein condensate existed. They and Wolfgang Ketterle, who did it independently with sodium, shared the Nobel Prize in 2001. Particles that behave the way Bose described are now called bosons, in his honor. Every particle in the universe is either a boson or a fermion, and the difference between them is precisely whether they are allowed to pile into the same state or forbidden from it. Fermions, like electrons and protons and neutrons, obey Pauli's exclusion and keep their distance, which is why matter has structure and volume. Bosons, like photons, are gregarious and will happily crowd into the same state in unlimited numbers, which is why you can have a laser, where a vast number of photons all march in identical step. Bose himself never won a Nobel Prize. When somebody asked him about it later, he said he had got all the recognition he deserved. Half the particles in the universe are named after him, which is not a bad consolation. Related things happen when you cool matter far enough, and they are among the eeriest sights in any laboratory. Cool liquid helium below about 2 degrees above absolute zero, and it becomes a superfluid. It has no viscosity whatsoever. Stir it, and it will keep rotating essentially forever. Put it in a beaker, and it will climb up the inside wall in an invisibly thin film, go over the rim, run down the outside, and drip off the bottom, emptying the beaker by itself. It will find its way through cracks too small for any ordinary liquid to pass. There is film of this, and it looks like a trick. Cool certain metals and they become superconductors, and electrical resistance does not merely get small, it goes to exactly zero. A current started in a superconducting loop will circulate for years without fading. Those are the magnets inside every MRI scanner in every hospital, which is why the machine needs its own supply of liquid helium and why it is so expensive to run. These are quantum effects made visible at human scale. Ordinarily, quantum behavior hides at the size of atoms, and the world above that looks classical. Cool things down enough and the quantum behavior comes up into the room with you, and helium climbs out of a cup. Now, the sun. There is a quantum effect I have been saving, because it is the one that touches you most directly, and it has one of the best names in physics. Tunneling. Picture a ball at the bottom of a valley and a hill on either side. Roll the ball and it goes partway up the hill and comes back down. To get over the hill, it needs enough energy to reach the top. That is obvious, and it is true for balls. For a quantum particle, it is not true. The particle is described by a wave, and when the wave meets the hill, it does not simply stop dead at the edge. It dies away inside the barrier, but it dies away gradually, and if the barrier is thin enough, a little bit of the wave is still there on the far side, which means there is a real probability that the particle is found on the other side, having never had enough energy to go over the top. It did not climb the hill. It did not smash through. It was simply, sometimes, found on the other side. The probability drops off ferociously fast as the barrier gets wider or higher, which is why you cannot walk through your bedroom wall. The odds are not zero in the mathematical sense. They are so close to zero that if every person who has ever lived spent every second of their lives walking into walls for the entire age of the universe, it would never once happen. So please do not try it. But at the scale of atoms, tunneling happens constantly, and it runs the sun. The sun makes its energy by fusing hydrogen nuclei together. Hydrogen nuclei are protons, and protons are positively charged, and like charges repel each other more and more fiercely the closer they get. To fuse, two protons have to get close enough for the strong nuclear force to grab them, and that means getting past an enormous electrical barrier. The center of the sun is about 15 million degrees, which sounds like plenty. It is not. Run the numbers with ordinary physics, and the protons in the sun's core do not have anything like enough energy to overcome that repulsion. Classical physics says the sun should not be burning. It says the sun should be a large cold ball of hydrogen sitting in the dark. What happens instead is that the protons tunnel. They approach. They do not have the energy to get over the barrier. And occasionally, rarely, one is found on the other side anyway, close enough to fuse. The probability for any given encounter is fantastically small, but there are an unimaginable number of protons in the core of a star, colliding an unimaginable number of times per second, and a fantastically small probability multiplied by an unimaginably large number of attempts gives you a steady, gentle, reliable output of energy, sustained for billions of years. Every star in the sky is shining because of a quantum loophole. The light you saw today, the warmth on your face if you stood in the sun at any point, arrived because particles in the core of a star did something that classical physics forbids, and then that energy takes an absurdly long time to get out. A photon produced in the core of the sun does not travel straight out. It is absorbed and re-emitted in a random direction over and over again by the dense plasma, taking a random walk that carries it a few millimeters at a time in no particular direction. The estimates vary widely depending on the model, but they are all on the order of tens of thousands of years for the energy to reach the surface. Once it gets out, it crosses 93 million miles of vacuum to your face in 8 minutes and 20 seconds. The sunlight that fell on you today began as a tunneling event in the dark center of a star. Took something like as long as the whole of human civilization to fight its way to the surface, and then took 8 minutes to reach you. Tunneling has other jobs, some of them extremely close to hand. Radioactive alpha decay is tunneling. An alpha particle sits inside a nucleus, trapped by a barrier it cannot classically escape, and it rattles around inside for what may be billions of years until one day it is simply found outside. That, incidentally, is exactly why radioactive decay has no cause you can point to. There is no internal clock, no wear, no aging. There is only a fixed probability per unit of time, which is why we talk about half-lives. Uranium in the ground is not counting down. Each nucleus, at every moment, has the same small chance of being found outside, and that is all there is to say about it. It is also, of course, precisely the mechanism Schrodinger put in the box with his cat. Flash memory works by tunneling. The storage in your phone and in a memory card keeps information by trapping electrons behind an insulating barrier that they should not be able to cross. To write and erase, the device deliberately pushes electrons through that barrier by tunneling. Every photograph on your phone is held in place by a wall that electrons are only allowed to cross when you ask them to. And the scanning tunneling microscope, invented in the 1980s, works by bringing an extremely fine needle so close to a surface that electrons tunnel across the gap. The size of that current depends so sensitively on the distance that you can map the surface atom by atom. It is the reason we have pictures of individual atoms at all. The first images of atoms arranged into letters were made by pushing them around with one of these. While we are down at that scale, there is one more idea worth having, and it is the modern one. Everything we have talked about tonight has been refined, over the second half of the 20th century, into something called quantum field theory, and its central picture is worth carrying with you. In quantum field theory, particles are not the fundamental things. Fields are. A field, in this sense, is something that has a value at every point in space. There is an electron field filling the whole universe, and a photon field, and a field for every kind of particle there is. And what we call a particle is a ripple in one of those fields, a localized excitation, a knot of vibration. An electron is a quantist ripple in the electron field. That is why every electron in the universe is exactly identical to every other electron, with precisely the same mass and charge, to as many decimal places as we can measure. They are not manufactured separately to a very tight specification. They are the same kind of ripple in the same single field, in the way that every wave on the same ocean is made of the same water. And it means the vacuum is not empty. A field cannot be perfectly still, for the same reason a particle cannot sit perfectly still, which is the uncertainty principle. So even in a region with no particles in it at all, the fields are quietly seething, with fluctuations flickering in and out of existence. Physicists call these virtual particles, though the phrase is a bit misleading, since they are really a way of talking about the fluctuations rather than a description of tiny objects popping into being. You might reasonably ask whether any of that is real, or whether it is a bookkeeping device. It is real, and we can measure it, and here are two ways. The first is the Casimir effect. Take two flat metal plates and place them extremely close together, a fraction of the width of a hair apart. In a vacuum, the plates are pushed together by a small but measurable force. The usual explanation is that the gap between them restricts which fluctuations can fit, so there is slightly more activity outside than inside, and the imbalance pushes them together. It has been measured repeatedly since the 1990s. The vacuum has a mechanical effect on real objects. The second is the Lamb shift. In 1947, Willis Lamb measured the energy levels of hydrogen with such precision that he found a tiny discrepancy from what Dirac's equation predicted. That tiny gap is caused by the electron interacting with the fluctuations of the vacuum around it. It is small, and it is exactly the size the theory says it should be. That comparison between what quantum field theory predicts and what the laboratory measures is where the theory earns its reputation. There is a quantity called the magnetic moment of the electron, and the agreement between the calculated value and the measured value runs to about 12 digits. No prediction in any science has ever been checked that hard and held. The equivalent, in more familiar terms, would be measuring the distance from London to New York and getting it right to within the width of a human hair. So this theory is not a loose philosophical story about how things might be. It is the most accurate description of nature human beings have ever produced, by an enormous margin. It is also, as we have seen, a description whose meaning nobody can agree on. Both of those things are true at once, and physicists have been living with the discomfort for 100 years. Come back up now, out of the vacuum, into the ordinary world, because the ordinary world is full of this. There is a claim that gets made about the 20th century, and it sounds like an exaggeration until you go through it item by item. Something like a third of the economy of the developed world depends directly on devices that could not have been designed without quantum mechanics. The transistor is the obvious one. A transistor is a switch with no moving parts made from semiconductors, and semiconductors only make sense in terms of quantum energy bands, the allowed and forbidden energy levels for electrons in a solid. Bohr's ladder, applied to a crystal instead of a single atom. Get that wrong and you cannot design silicon. The first transistor was built at Bell Labs in 1947 by John Bardeen, Walter Brattain, and William Shockley, and everything digital descends from it. There are more transistors in the phone beside your bed than there were grains of rice in the harvest of a medieval kingdom. And every one of them is a piece of applied quantum theory. The laser is another. The idea comes directly from Einstein in 1917, when he worked out that an atom sitting in an excited state, hit by a photon of exactly the right energy, will emit a second photon identical to the first, traveling in the same direction, in step. Stimulated emission. Do that in a chamber with mirrors and you get an avalanche of identical photons all marching together, which is a laser beam. It took until 1960 to build one, and when Theodore Maiman built it, the joke was that it was a solution looking for a problem. It is now in every supermarket scanner, every fiber optic cable carrying this narration to you, every eye surgery, every distance measurement to the moon. The lead in the lamp beside you is a quantum device. Electrons drop across an energy gap in a semiconductor and emit a photon whose color is set by the size of the gap, which is Bohr's principle again. Red and green were easy. Blue took decades and a great deal of stubbornness, mostly by Isamu Akasaki, Hiroshi Amano, and Shuji Nakamura, who shared the 2014 Nobel Prize for it. Blue was the missing one, because without blue you cannot make white light, and without white LED light you cannot replace the bulb. Almost every light in your home is now the result of that. MRI scanners work on the quantum spin of protons in the water in your body, flipped by radio waves inside a superconducting magnet. Atomic clocks work by counting the oscillation of a specific quantum transition in cesium atoms, which is so regular that the second itself is now defined by it. And GPS depends on those clocks and on correcting them for both special and general relativity, so that the position on your phone is accurate to a few meters rather than being wrong by kilometers by the end of the day. Solar panels are the photoelectric effect, industrialized, Einstein's 1905 paper, on a roof. None of this was foreseen. Not one of the people we have met tonight was trying to invent any of it. Planck was solving a lighting standards problem. Bohr wanted to know why atoms do not collapse. Dirac wanted a beautiful equation. Pauli wanted the arithmetic to add up. The technology arrived later from people who read their papers, which brings us to the thing everyone has heard about and almost nobody has been told accurately, which is the quantum computer. An ordinary computer stores information in bits, and each bit is either a 0 or a 1. A quantum computer uses quantum bits, called qubits, and a qubit can be in a superposition of 0 and 1. Now here is where the popular explanation goes wrong, and it goes wrong every single time. You will be told that because a qubit can be 0 and 1 at once, a quantum computer tries every possible answer simultaneously, and that a machine with 300 qubits explores more possibilities than there are atoms in the universe, all at the same time, and that this is why they will be so fast. That is not how it works, and it is worth knowing why, because what really happens is more elegant. The problem with trying every answer at once is that you cannot read them. When you measure a quantum system in a superposition of 1 trillion possible answers, you get one of them, at random. You do not get a list. You get a single sample, and it is almost certainly not the one you wanted. A machine that computes every answer and then hands you a random one is worthless. What a quantum algorithm actually does is much cleverer. It arranges the calculation so that the many possibilities interfere with each other. Remember the double slit, where crests met troughs and cancelled, and crests met crests and reinforced. A quantum algorithm is designed so that the paths leading to wrong answers cancel each other out, and the paths leading to right answers reinforce. Then when you measure, the right answer is what is overwhelmingly likely to come out. That is a much narrower tool than the popular version, and it is why quantum computers are not simply faster computers. They are only useful for problems with the right kind of structure, where such an interference pattern can be arranged. There are a few known, factoring very large numbers, which is what worries cryptographers, searching unstructured data with a modest speed-up, and above all simulating quantum systems themselves, which is the thing they will almost certainly be genuinely transformative at. Because chemistry and materials science and drug design all involve modeling quantum behavior, and ordinary computers are terrible at it. Feynman suggested exactly this in 1981, saying that if you want to simulate nature, you had better make your simulator quantum mechanical. Your email is not going to arrive faster. Your video will not render faster. That is not what these machines do. The great enemy is decoherence, which we met earlier. To compute, the qubits have to stay in superposition and stay entangled with each other and not with anything else, and the universe is constantly leaking information out of them. Every stray vibration, every particle of infrared light, every magnetic wobble destroys the calculation. This is why the machines sit inside refrigerators colder than deep space, and why the photographs always show that beautiful gold chandelier of tubes, which is the cooling system, not the computer. The actual chip is a fingernail-sized thing at the bottom. The answer to decoherence is error correction, and this is where the field genuinely is at the moment. The idea is to spread the information of one reliable logical qubit across many unreliable physical qubits, so that errors can be spotted and fixed without disturbing the calculation. The trouble is that error correction machinery introduces errors of its own, and for decades the question was whether you could ever get above the break-even point, where adding more physical qubits makes the logical qubit better rather than worse. Below that threshold, you make things worse by making them bigger. In December of 2024, Google published results from a chip called Willow, with 105 physical qubits, showing that they had crossed it. When they increased the size of the error-correcting code, the error rate went down rather than up, roughly halving with each step, and the encoded qubit outlived the best individual physical qubit in the chip. It is the milestone the field had been chasing since Peter Shor's work in 1995. One of the Google researchers summarized it simply, saying they were finally below the threshold. In June of 2025, IBM published a roadmap for a machine called Starling, targeted for 2029, intended to run circuits of 100 million quantum gates on 200 logical qubits. And now the honest part, because there is an enormous amount of noise around this subject and some of it is being sold to investors. As of now, quantum computers cannot do anything commercially useful that an ordinary computer cannot do better. Not one thing. The demonstrations of quantum advantage so far have been on artificial problems designed specifically to be hard for classical machines and easy for quantum ones, and several of them have subsequently been matched by clever classical algorithms. What happened in 2024 was that a long-standing engineering barrier fell, which is genuinely enormous, and which suggests the machines will eventually work. Eventually is doing real work in that sentence. The field is at roughly the stage the transistor was at in the early 1950s, when it existed and functioned and nobody had built a computer out of it yet. That is not a criticism. That is what the beginning of something looks like. Now, before we start letting the evening go, there is one more place to look, and it is the strangest of all, because it is alive. The question is whether biology uses quantum effects deliberately. Not incidentally, since all of chemistry is quantum in the trivial sense, but genuinely, in a way that evolution has shaped and depends on. The honest answer as of now is one clear yes, one exciting maybe, and one no that used to be a headline. Start with the yes, because it is solid and unglamorous. Enzymes, the proteins that make the chemistry of life run at speeds it otherwise could not, use tunneling. Specifically, they move hydrogen from place to place, and hydrogen is light enough that tunneling matters. And there is good evidence going back to work by Judith Klinman and others that some enzyme reactions proceed by hydrogen tunneling rather than by hydrogen going over the energy barrier. Life uses the loophole. Every cell in your body is doing it right now. Now the maybe, and it is a lovely one. Many birds navigate using the Earth's magnetic field, and it has been known for decades that in several species the magnetic compass only works if there is light of the right color hitting the bird's eye, which is a very odd requirement for a compass. Magnets do not need light. The leading explanation is called the radical pair mechanism, proposed by Klaus Schulten in 1978 and developed since. The idea is that a photon strikes a protein called cryptochrome in the bird's retina and knocks an electron across, leaving two molecules each with an unpaired electron, and those two electrons are quantum mechanically entangled. The pair can be in either of two spin arrangements, and which one it settles into affects the chemical reaction that follows, and the balance between them is sensitive to the direction of the surrounding magnetic field. So the chemistry in the eye ends up depending on which way the bird is facing, which would mean, if it is right, that the bird sees the magnetic field, that it is laid over its vision as a pattern of light or shade that shifts as it turns its head. In 2021, a group published a study in Nature on cryptochrome taken from the eyes of European robins, a migratory species, and showed that in a test tube the protein's photochemistry is indeed sensitive to magnetic fields, and that it is more sensitive than the equivalent protein taken from chickens and pigeons, which do not make long migrations. That is a beautiful result, and it is not the finished argument, and the researchers were careful to say so. It was done in vitro, on isolated protein, using magnetic fields stronger than the Earth's. Whether this is the sensor in the living bird, and how the bird's brain reads it, is not established. One of the authors put it plainly, saying that how the bird perceives this, they do not know. So the correct thing to say is that a bird flying over your house tonight, heading south, may be navigating using entangled electrons in its eye. May. It is the most promising hypothesis anyone has, and it is not proven, and the people doing the work will tell you so. Now the one that used to be a headline in 2007, an experiment on a light-harvesting protein complex from a photosynthetic bacterium, seemed to show long-lived quantum coherence, and it was immediately reported everywhere as evidence that plants are quantum computers, that photosynthesis explores all possible routes for energy simultaneously and picks the most efficient one. It was a wonderful story, and it appeared in a great many books. It has largely fallen apart. Careful remeasurements, particularly from around 2017 onwards, found that the purely electronic coherences last something like 60 femtoseconds, which is 60 millionths of a billionth of a second, far too brief to steer anything. The oscillations that were seen in the original data are now generally attributed to vibrations in the molecular structure rather than to the coherent electronic effect that was claimed. A consensus review published in 2020 by a large group of researchers in the field stated it directly that those coherences are too short-lived to contribute to the efficiency of photosynthesis. I mention it because it matters that a story like this gets corrected out loud. It is still repeated constantly in popular accounts, and it is one of those cases where the exciting version and the true version have parted company. Photosynthesis is extraordinarily efficient by ordinary chemical means, which is impressive enough. And there is a fourth claim, about smell, which proposes that your nose detects the vibration of molecules by electron tunneling rather than their shape. It is an ingenious idea. It has a devoted advocate in Luca Turin, and the experimental tests have mostly gone against it. The mainstream view remains that receptors respond to molecular shape. File it as interesting and probably wrong, which leaves the question we have been walking around all night, and which nobody can answer. What is actually going on? The mathematics works. It works to 12 decimal places. It gave us the transistor and the laser and the scanner and the clock. Nobody disputes any of that. What is disputed is what the mathematics is telling us about the world, and there are several serious answers, held by serious people, and no experiment has ever separated them. This is not a fringe disagreement. It is the central unresolved question in the foundations of physics, and it has been open for a century. I am going to lay out the main ones fairly, and I am not going to tell you which is right, because nobody knows. The first is the Copenhagen interpretation, which we met, and it is the one in the textbooks. The wave describes what we can know. When we measure, we get one outcome. Do not ask what the particle was doing in between, because the question is not meaningful. Its great strength is that it is honest about the limits of the theory and it lets you get on with your work. Its great weakness is that it draws a line between the quantum world and the classical world of measuring devices and never says where that line is or what puts it there. Physicists sometimes summarize the working attitude as shut up and calculate, which was probably coined by David Mermin, and which was meant as a criticism and got adopted as a slogan. The second is many worlds, and it comes from a graduate student who was ignored. Hugh Everett III was working under John Wheeler at Princeton in the mid-1950s, and he asked a question of admirable simplicity. Why do we add a collapse at all? The Schrodinger equation does not collapse anything. We put the collapse in by hand because we only ever see one outcome. What if we take the equation completely literally and never collapse anything? Then when you measure a particle in a superposition, you do not force it to choose. You become part of the superposition. There is now a version of you that saw the first outcome and a version that saw the second, and they no longer interact with each other, and each one feels like the only one. The universe does not choose. It contains all the branches. Forever, it sounds extravagant, and it is. But notice what it buys. There is no collapse, no special role for measurement, no line between quantum and classical, no randomness in the fundamental description. The equation runs, and only the equation. Some very good physicists find that a much cleaner picture than adding a mysterious process that nothing else in physics does. The cost is an unimaginable number of universes you can never see or reach. Wheeler took the thesis to Bohr in Copenhagen. Bohr was not interested, and the reception was cold enough that the thesis was cut down to about a quarter of its length to soften the disagreement, and it sank almost without trace. Everett was 27. He left academic physics entirely and never went back. He went to work for the Pentagon, doing mathematical analysis of nuclear war, calculating fallout and casualties in the event of exchanges, which is an unusual place for a man who believed that every possible outcome happened somewhere. He was very good at it. Later, he ran his own software company. He drank heavily, ate badly, chain-smoked, and had no interest in his own health. He is reported to have believed in a version of his own theory sometimes called quantum immortality, in which the observer always finds themselves in a branch where they survived. He died of a heart attack in 1982 at 51. He was a committed atheist, and he had asked that his ashes be thrown out with the rubbish. His wife kept them in a filing cabinet for a few years, and then did what he had asked. His daughter Elizabeth had struggled with mental illness for years, and she died by suicide in 1996. She left a note asking that her ashes be thrown out with the rubbish as well, so that she might end up in the correct parallel universe to meet up with her father. His son had a different path. Mark Oliver Everett, who found his father's body when he was 19, became a musician and fronts the band Eels, and eventually made a documentary for the BBC about the father he had barely spoken to, traveling around the world meeting physicists who could explain to him what the man at the kitchen table had been thinking about. Everett lived just long enough to see his idea start to be taken seriously. Today, many worlds is one of the leading interpretations, taken seriously by cosmologists in particular, and there are surveys of physicists in which it comes second only to Copenhagen. He was invited back to speak once, in 1977, at the invitation of a younger physicist who admired the work. He gave a talk. It was recorded. Then he went back to his defense contracts. The third interpretation is the pilot wave, and it belongs to David Bohm, whose life was also broken by the 20th century, though in a different way. Bohm was American, a brilliant young theorist who had worked at Berkeley under Robert Oppenheimer. He had been involved in left-wing politics as a student, and in 1949 the House Un-American Activities Committee called him to testify about colleagues, including Oppenheimer. He refused on constitutional grounds. He was arrested and charged with contempt of Congress. He was acquitted at trial in 1951, and it made no difference. Princeton had already suspended him. They did not renew his contract, and no American university would touch him. He left the country. He went to Brazil, where the American authorities confiscated his passport, then to Israel, and eventually to Britain, and he never worked in the United States again. And in 1952, in exile, he published a version of quantum mechanics that everybody had been told was impossible. In Bohm's picture, particles are real, and they have definite positions at all times, and they follow definite paths. There is no collapse and no fuzziness about where things are. What guides them is a wave, a real physical wave which fills space and steers the particle. In the double slit, the particle really does go through one slit, and the wave goes through both, and the wave is what produces the interference pattern by guiding the particle. Everything comes out the same as standard quantum mechanics, every prediction, exactly. The price is that the guiding wave is non-local. What the wave does here depends instantly on the configuration of the whole system, including parts of it far away. Bohm accepted that price openly. Most physicists ignored it, partly because there had been a famous proof by John von Neumann that hidden variable theories were impossible, and Bohm's theory clearly existed, so the proof had to be wrong somewhere. It was. Bell found the flaw, and it was seeing Bohm's theory do the impossible that set Bell off on the road to his own theorem in the first place, which is a nice piece of history. Bohm's exiled, ignored theory is the reason we have the deepest result in the field. There are other positions worth naming briefly. Objective collapse theories, of which the best known is called GRU after its three authors, propose that collapse is a real physical process that happens spontaneously, extremely rarely for a single particle, but so often for a large object with countless particles that it is effectively instantaneous. That would explain why small things stay in superposition and big things do not, without any observers at all, and unlike every other interpretation on this list. It makes slightly different predictions from standard quantum mechanics, which means experiments are being done right now to look for it. That is its great virtue. It can be tested. Then there is cubism, which takes the wave function to be a description of a particular agent's information and expectations rather than a description of the world. So that collapse is just what happens when you update your beliefs on new evidence. And relational quantum mechanics, from Carlo Rovelli, in which a system's properties exist only in relation to other systems, so that there is no such thing as the state of a particle full stop, only the state of a particle relative to something else. They cannot all be right. All of them reproduce every experiment ever done, and the community is genuinely split, which you can see in the informal polls that get taken at foundations conferences, where the vote scatters and there is no majority for anything. 100 years, the most successful theory in the history of physics, and we do not know what it means. There is something quite restful about that if you let it be. There is more we do not know, and it is worth saying out loud before the night closes. The largest gap is that quantum mechanics and gravity do not fit together. Everything we have discussed tonight sits inside quantum theory. Gravity sits inside Einstein's general relativity, where gravity is not a force at all, but the curvature of space and time. Both theories are extraordinarily well tested in their own domains, and they are built on incompatible foundations. and when you try to apply both at once, in the two places where you have to, at the center of a black hole and in the first instance of the universe, the mathematics produces nonsense. Infinities where numbers should be. There are candidate theories, string theory, loop quantum gravity, others. None of them has produced a prediction anyone has been able to test. It has been an open problem since roughly the 1930s. The measurement problem is still open, as we have seen, and there is a question that sounds almost childish and is completely serious, which is why quantum mechanics at all? Why this structure, with these probabilities, this Planck constant, this particular graininess? Nobody has derived it from anything deeper. We found the rules by being backed into them, one reluctant step at a time, by measurements that would not behave. Planck was 17 when he was told there was nothing important left to discover, something in that ought to keep us modest. So let us bring it home, and let it get quiet now. You are lying down. Underneath you there is a mattress, and it is holding you up, and the reason it is holding you up is that the electrons in it and the electrons in you refuse to occupy the same states, not because they push each other electrically, though they do a little, but because of a rule Wolfgang Pauli found in 1925, in the middle of the worst period of his life. The firmness underneath you is that rule. You have been leaning on it your whole life. The atoms you are made of are stable, and have been stable for billions of years, because electrons in an atom can only sit on certain rungs, and there is a lowest rung, and nothing can fall below it. That is Bohr, in 1913, trying to work out why matter does not collapse in 100 millionth of a second. It does not collapse. You are the evidence. Every chemical reaction keeping you alive tonight, in your liver, in your blood, in the cells of your eyelids, runs on the arrangement of electrons in outer shells, which is the periodic table, which is Pauli again. Some of the enzymes doing that work are moving hydrogen atoms through barriers they cannot climb, by tunneling thousands of times a second, in the dark, without being asked. If you were outside today, the light that touched your skin came out of a star, and it only exists because protons in the core of that star went through a wall they had no right to pass. That energy spent something like tens of thousands of years working its way to the surface of the sun, longer than there have been cities, longer than there has been writing. Then it crossed the space between us in 8 minutes and 20 seconds, and landed on the back of your hand while you were thinking about something else. Right now, while you lie there, about 60 billion neutrinos are passing through each square centimeter of you every second, and at this hour most of them have come up through the entire body of the Earth to reach you, because the planet does not slow them down. They are going through the pillow, through your skull, through the thought you are having, and out into the sky on the other side. And they will not touch anything for a very long time. And somewhere in the dark outside, if it is the right season, there may be a small bird flying south with a protein in its eye that responds to the magnetic field of the planet, possibly by way of 2 entangled electrons, seeing something that we cannot see and cannot yet fully explain. The people who found all this out were not calm, well-organized geniuses working in good conditions. A young man with his face swollen shut, alone on a bare rock in the North Sea, sat up until 3 in the morning and found that the numbers worked. A middle-aged Austrian went up a mountain with a woman whose name is lost and came down with the central equation of the theory. A silent Englishman who had been punished for his grammar as a child trusted a piece of mathematics over the advice of everyone he knew and found the mere half of matter. A technician's son from Belfast, working on his holidays because the subject was not respectable, settled the deepest argument in physics, and a German professor in a black frock coat, who had been told as a boy that there was nothing left to find, found the grain of the universe and spent 30 years wishing he had not, and then lost almost everyone he loved. They were all guessing and checking and getting it wrong and going back. The picture they left us is not the one anyone wanted. It says that at the bottom. Things do not have definite positions until something interacts with them, that the world comes in grains rather than in a smooth, continuous flow. That certainty of the old kind is not available, not because we are not clever enough yet, but because the world is not built out of that material, and that two things that have touched each other once remain connected in a way that no arrangement of ordinary objects can imitate, across any distance, forever, without ever being able to send each other a word. You do not have to hold on to any of it. Nothing here needs remembering. Whatever is left of the day is loosening now. Your breathing has already slowed without you deciding to slow it. The hum of restlessness at the bottom of all matter, the jitter that cannot be stilled even at absolute zero, is going on quite happily in every atom of you, and it has never once needed your attention. The bed holds you up because electrons will not share. The light that warmed you today came through a wall it could not climb. And you, lying still in the dark, are a very large number of grains of a world that nobody has finished explaining, arranged for the moment in this particular shape, breathing slowly, going under. Sleep now. It will all still be unsolved in the morning.